Hello everybody and welcome to this introductory video to organic chemistry for A-level chemistry. This is going to be a three-part introduction, and in this session this morning we're going to be looking at formulae and homologous series. In subsequent videos we will look at nomenclature, so that's naming organic molecules. That's going to be in the second video, and in the third video we're going to be looking at isomerism. Now, organic chemistry is the study of millions of covalent compounds of the element carbon. These structurally diverse compounds vary from naturally occurring petrol fuels to DNA and the molecules in living systems. Organic compounds also demonstrate human ingenuity in the vast range of synthetic materials created by chemists. Many of these compounds are used as drugs, medicines, and plastics. And in the search for sustainable chemistry, for safer agrochemicals, and for new materials to match the desires for new technology, chemistry plays the dominant role. I said that organic chemistry is a study of carbon compounds, so it's worth taking a look at the bonding in organic compounds, focusing on carbon in this first instance. Now, carbon is in group 4 of the periodic table. And so this means that it's got 4 electrons in its outer shell. And since it's got 4 electrons in its outer shell, it therefore needs 4 more. And what that does is that allows it to have its full outer shell of 8. To do this, carbon therefore forms 4 covalent bonds, and that makes it become stable. So carbon has 4 covalent bonds, and this makes it stable. Now there's 3 ways that it can do this. The first one is definitely the most common. It can have 4 single covalent bonds. And this is the case in simple carbon compounds such as methane, and in other compounds such as methanol. Alternatively, it could have 2 single bonds and 1 double bond. And this is the case in molecules such as ethene. And what you'll notice is it does still have a total of 4 bonds. We've got 2 bonds here in the middle, and then a 3rd bond here, and then a 4th bond here. So this carbon on the left-hand side has got 4. If we consider the carbon on the right-hand side, it's got 4. 1, 2, 3, 4. And this carbon up at the top, 1, 2, 3, 4. So carbon always has 4 covalent bonds. You'll notice as well that hydrogen, this hydrogen here, has got 1 bond. This hydrogen here also 1. Hydrogen always has 1, and oxygen has got 2 up here. And oxygen always has 2. And the last combination, it might only have, a carbon atom that is, might only have 1 single bond and 1 triple bond. And this is much rarer, and you're likely to come across it in only a few places in A-level chemistry. And an example of that is this molecule here, which is ethine. And you can see that we've got 1, 2, 3, 4 bonds for the carbon on the left, and it's the same for the carbon on the right. Let's take a look at the different types of formula that you might be expected to work with for organic molecules. There are 6 different types of formula, although the last one is a little bit different to the others. So there's empirical formula, molecular formula, displayed formula, structural formula, skeletal formula, and general formula. Just to say something about the word formula itself, if it ends in LA, this is the singular. And so we might be talking about one formula or type of formula. and if it ends in AE, it's pronounced Formulae, and this is talking about the plural, and the plural there, we mean two or more formulas, but we wouldn't say formulas, we'd say formulae, or types of formula. And we'll have a look now in more detail about each one of these different types of formula. First up, we're going to take a look at molecular formula. And now molecular formula is probably what you're most familiar with because it gives the actual numbers of atoms of each element in a compound. Now, for example, if we considered, well, let's just write a few formulas. C6H12, that means there are 6 carbons and 12 hydrogens. C4H8, that means 4 carbon and 8 hydrogen. C2H6, C6H6, C6H12O6, and C2H4O2. These are all different formulae, and they show how many atoms of carbon and how many atoms of hydrogen, and in some cases how many atoms of oxygen there are in these molecules. And I'll finish with C3H8 on there. So these 8 are all molecular formula. They tell us precisely how many atoms of each element there are in a compound. Now, if we have a look at empirical formula now, empirical formula is defined as the simplest whole number ratio of atoms of each element in a compound. So you'll notice that those two definitions seem really similar, and the only differences between the two definitions are those bits that I've underlined. So where the molecular formula gives the actual numbers of atoms of each element in a compound, the empirical formula gives us just the simplest whole number ratio. And so, for example, CH2. That acknowledges the fact that there is only 1 carbon for every 2 hydrogen atoms in the molecular formula. Now you'll notice that the relationship between the two formulae is an integer multiple. So for here, if we divide the molecular formula by 6, we get to the empirical formula. Now the empirical formula for this second one is exactly the same, and you'll notice that we can work between them by dividing by 6 or multiplying by 6 for the first one, and the second one we're multiplying by 4 or dividing by 4, depending on which direction we are going in, whether we're converting the molecular formulae on this side into the empirical formulae on this side. We'll be dividing if we go that way. If we're converting the empirical formula to the molecular formula, we'll be multiplying by going the other way. So these empirical formulae on the right hand side, CH3, because we've needed to divide this one by 2. This one, the simplest integer is 6, and so we can get CH on here. This one is also 6 because we've got the numbers 6 and 12 and 6, so we're looking to divide that by the biggest number that we can, which is 6, and we get CH2O. Now this time we've got 2, 4 and 2, so we're trying to divide that by the biggest number that we can, which is 2, and so CH2O. So you can see that we've got the same empirical formula, but we've got different molecular formulas on this side. So different molecular formulas, but the same empirical formulas. Now, there are some occasions, like these bottom two, where the empirical formula is the same as the molecular formula. And that's because there is no number that 3 and 8 can divide by to get smaller integers in there. We can't divide them by 3 or 4 or anything like that. And so the empirical formula and the molecular formula can sometimes be the same. Let's take a look now at how we can work out the empirical formula of an organic compound. More about this in the amount of substance video, but for now let's look at one example. And so let's imagine we've been asked this question. 5.80 grams of propane contains 4.80 grams of carbon and 1.00 grams of hydrogen, and our command is what is the empirical formula? So we're going to set this out in a similar sort of way to a reacting mass calculation. And we need to have the elements that are in the compound along the top. There's only 2, so we can use plenty of space. Squash them up a bit more if there were 3. And then down the left-hand side, we need to always use this structure. We've got the mass, or the percentage, in this case it's mass. Then we've got the relative atomic mass. Then we've got the moles. And last of all, we've got the mole ratio. And so to start putting the numbers in, we know we've got 4.80 grams of carbon and 1.00 grams of hydrogen. The relative atomic mass of carbon is 12.0 and hydrogen is 1.0. And so therefore moles, which we know is mass divided by relative atomic mass, is 4.8 divided by 12 for carbon, which is 0.4. And then for hydrogen, it is 1 divided by 1, which is of course 1. Then to turn something into its mole ratio. Now, the way that we do that is we must divide it by the smallest, which on this instance is of course 0.4 for the carbon. And so the mole ratio is 0.4 divided by 0.4, which gives us 1. And then on the right hand side we've got 1 divided by 0.4, and this is 2.5. So now we don't have a whole number here, so we need to scale that up because we can't do any rounding here. We're not allowed to round that at all. So we need to scale up. Now we know that 2.5 is obviously 2.5, and so if we double that, we're going to get a 5, and we have to of course double this one as well, so we get 2. And so we've got a ratio of 2 to 5 for carbon to hydrogen, and that can't be reduced any further. And so the empirical formula is therefore C2H5. And a final part to this skill, you might be required to convert an empirical formula into a molecular formula. Now to do this, there are two things that you need. You must have either been asked to work out the empirical formula or been given it in the question, and you must also have been given the relative formula mass, or the MR, of the molecule, or I guess you could also have been shown a mass spectrum and be asked to spot the molecular ion peak from it, which is the peak with the heaviest mass, which is the one on the right hand side, and that is the MR of the molecule. So let's take the empirical formula that we calculated in the previous page of C2H5, and let's imagine we've been given the MR of 58. And so the three steps that we have to do now is we have to look at the empirical formula and work out what the empirical formula mass is. So that's 12 for each of the carbon atoms and 1 for each of the 5 hydrogens. That's a total of 5. And so that gives us a total of 29 is the mass of the empirical formula. Step 2, we have to work out what that whole number multiple is that turns the empirical formula into the molecular formula. What is it that we're multiplying the empirical formula by? Now to do that, we just need to work out how many times bigger the molecular formula is than the empirical formula. And so we take the molecular formula mass and we divide it by the empirical formula mass, which is on this occasion 58 divided by 29, which is 2. And what that means then is that the molecular formula equals twice as big as the empirical formula. And so our final task is to state what the molecular formula is. We must always remember to do that after we've done the hard work. The molecular formula is C4H10. And so what it is that we're doing is we're multiplying those numbers at the bottom by 2. So C2 becomes C4, H5 becomes H10, because the molecular formula is actually twice as big as the empirical formula. Other different types of formulae are used in organic chemistry because there's such a rich variety of different organic molecules when you compare it to inorganic compounds. You need to pay careful attention to the exam question to notice what type of formula you're being asked to use. Now let's have a look at displayed formula, which is probably the easiest type to use. Now what displayed formula does is it shows all the atoms and all the bonds present in a molecule. If we have a look at these examples, you can see we've got methane up here, which has got 1 carbon atom in the middle and 1, 2, 3, 4 bonds for the carbon, 1 for each of the hydrogen, and we've got this molecule here, which is methanol, and we can see all the atoms in each case that are present in the molecule and how they are bonded together. So in many ways, displayed formulae gives us the most information, but it's actually the longest one to draw. I drew all of these whilst I paused my recording because it takes such a long time and it's not very exciting to watch somebody draw all of these different formulae. And so there are two different faster ways of representing formulae rather than using displayed formula. The first of these is structural formula. Now what the structural formula does is it shows the actual arrangement of atoms in a molecule without showing many bonds at all. So very few bonds are shown. Now the good thing about structural formula is it's faster and it does still give you good information about the arrangement of atoms in a molecule, and we can say that it is unique for each molecule. So each molecule has its own unique structural formula. Let's take a look at these displayed formulae and let's turn them into structural formulae. So how you do that is really straightforward. You just sort of read left to right what the molecule contains and kind of group the atoms together around the central carbon. Let's take a look at this first molecule here, this ethane molecule. On the left-hand side we have got carbon number 1, and carbon number 1 has got 3 hydrogen atoms around it. And so what we do is we just write CH3. Carbon number 2 has also got 3 hydrogens around it, so we write CH3 again. And so the structural formula for ethane is just CH3, CH3. So there is one group after another that is identical. If we move on to this second one, again, reading left to right, we've got a CH3 group again. On the right-hand side, it's a little bit more complicated, but not much. We don't have a CH3 this time. Focusing again around that central carbon, we've got a CH2, and then we've got a chlorine also attached to it. And so the convention is you indicate the hydrogen atoms that belong to the carbon first, and then you add any additional atoms, like the chlorine in this case, onto it as well. So if we move along to our third example here, we've got a CH3 group, nice and easy again. Then on the middle carbon, we've got 1 hydrogen, so we write CH, and then this time we've got an OH group attached as well to that middle carbon. So notice that we don't write CH2O because that would imply that the 2 hydrogens are both attached to the carbon. So we write CH because that H is attached to the carbon. And then we write the OH separately because that is one distinct group, the OH attached to that carbon. And then at the end there we have got CH3 group. Again, I've missed a hydrogen off, but that should be a CH3 group at the end. Now if we have a look at this last example, structural formula for alkenes, there are usually 2 options for you, but in this case what I would encourage you to do is just simply write CH2 for the left-hand carbon, and for the right-hand carbon we've also got a CH2. So that's a structural formula for ethene. You could alternatively show that double bond between those 2 carbons, but this one on the left-hand side would be my preference. This next type of formula, called skeletal formula, is my favourite, mostly because it is significantly faster than the other 2, but also it does give more information than the other 2, even though actually there's fewer things there. So first up, you don't actually draw the carbon atoms at all, which seems strange. Not only that, you don't show any of the carbon to hydrogen bonds at all. And so what you get, if you have one of these, displayed formulae here, and this is propane, the skeletal formula for this, you just do a zigzag line like that. Now this looks really funny, but what this is a line that represents the carbon atom. So that carbon atom is this carbon atom here. This carbon atom is this one, and this carbon atom is here. And so at each vertex, which is where 2 lines meet, you've actually got a carbon atom. So we're kind of showing that only we're being really lazy and not showing the carbon atoms, and so it ends up looking like that. And so not only are we being really lazy and not drawing the carbon atoms, we're not showing those 3 hydrogen atoms that are left over as well. What we do is we assume that each carbon has 4 bonds, and we're just not showing those carbon to hydrogen bonds. So if we can only see, for instance, in this case here, we can only see that there is one line between our 2 vertices. That suggests that the carbon has got one bond to another carbon, and we're just not showing the 3 carbon to hydrogen bonds. So we add enough carbon to hydrogen bonds in our kind of minds to know that the carbon has got 4 bonds in total. If we take a look at this next one, this is an alkene, butene, we need to go through the same motions. We've got 1, 2, 3, 4 carbons. So to do that, we do a line like that. 1, 2, 3, 4 carbon atoms. We don't show any of the bonds to the hydrogen atoms, but what we do need to acknowledge this time is the fact that there is a double bond here between the first and second carbon atoms, and so to do that, we just add what effectively ends up looking a bit like an equal sign between the first and second kind of vertices of our line. And so we've got 4 carbons still. There's one here, there's one here, one here, and one here. And there are all those other 8 hydrogen atoms as well, with those 8 carbon to hydrogen bonds, 2 coming off here, another 1 coming off there, 2 coming off here, and 3 coming off here. We just don't show them. If we have a look at one last example on this page, this amine that's here, we do this in the exact same way. This time we only have got 1, 2 carbon atoms, so we show that with a line. Looks really weird just drawing a line. That would be ethane, what I've drawn there. And then we need to add this amine group on here. Now to add other functional groups, all you do is you draw a line down to it and you just write the functional group in its structural formula, so NH2 on there. And so this is in fact the structural formula for this ethyl amine that I had drawn here. So you can see that skeletal formulae, I should say, this is the skeletal formula. And skeletal formulae are much faster, but they are more complicated. So because skeletal formulae are more complicated, I have got 6 examples here that maybe you could have a go at if you feel confident, or you could just watch me create them as well. So let me have a go at these skeletal formulae. So this first one is nice and easy. We've got 4 carbons in a row, so actually all we need to do is that. This second one's a little bit harder. We've only got 3 carbon atoms in a row, so we're going to draw this, but because it is an alkene, we've got that line there. This next one, we've got 3 carbons in a row, so we're going to draw a triangle again, like that. But we've got a bromine atom on the second carbon, and so we need to have a bond coming off here, pointing to a bromine. This fourth one, we've got 1, 2, 3, 4 carbon atoms in a row, and then we've got this alcohol group, an extra group sticking out, and so we draw a line going down to it, and then we write the OH like that. This amine on the left-hand side is actually identical to one that I showed you earlier, so let's just change it to a slightly longer amine, propyl amine. And then to turn this into skeletal formula, we've got 1, 2, 3 carbon atoms now, so 1, 2, 3, down like that, 1, 2, 3, and then the NH2 group sticks out here. If we just take a look at this bottom one now, we've got 2 carbon atoms here and here, and so we do a single line like that, and then we've got this interesting functional group where there's a double bond O sticking out, and so we need to come down like that, make sure that's connected, and the oxygen goes in there. And we don't show any of the carbon to hydrogen bonds at all. We don't even show that one, which would be up here, but we don't show it. We just simply show the carbons as these kind of vertices at the where 2 lines might meet, and we show the interesting functional groups like the OH and the NH2, and in this case the C double bond O. The final thing to say about skeletal formulae, another reason why it's better, is it gives us a better idea about the angles between the bonds and the 3-dimensional shape of the particular molecule, because this picture up here, for instance, gives us a 90-degree bond angle between that carbon to hydrogen bond and that one. and similarly between that C to C bond. What we actually get in reality is closer in our drawing to the reality, which is 109.5 degrees is what this angle should be. They're not all perfect still, because this angle here should be closer to 120 degrees, in fact. But it is closer to the truth. So to summarise these 5 formulae that we've been looking at, we've got the empirical formula, which is the simplest ratio of atoms of each element in a compound, the molecular formula, which shows the actual numbers of atoms of each element in a compound, displayed formula, which shows all of the atoms and all of the bonds. The structural formula doesn't show many of the bonds, if any, but it does show the arrangement of the atoms. And the skeletal formula, which doesn't show the actual identity of any of the elements directly, but the zigzag line gives us our carbon skeleton, and we do have functional groups branching off from that carbon skeleton. Let's move on now to look at something called homologous series. Now this is a family of compounds that have all got the same functional group, but different chain lengths. Now I've been using the word functional groups before, and what a functional group is, it's the atom or the group of atoms that are responsible for the characteristics of the molecule, or perhaps most pertinently, the reactivity of the molecule. We'll have a look at each family in turn, but let's just give a few examples of these families. So we've got alkanes, we've got alkenes, and we've got alcohols. They're all 3 different families, and they've all got some characteristic properties. So they've all got the same functional group, I've already mentioned that, and as a result of having the same functional group, they've got the same chemical properties. Not only do they have the same chemical properties, they also have the same general formula. And I'll explain what the general formula is in more detail for each particular homologous series, each particular family. But for instance, for the alkene, the functional group is CnH2n. And so what that means is, if you know how many carbon atoms you've got, which let's just make it 3, the hydrogen atoms will be twice as much, 2 times by 3. So it will be C3H6, and C20H would be 2 times by 20, which is 40, so C20H40. That's what we mean by the general formula. As you work your way through the homologous series, each member is longer by CH2 each time. What you're adding as a chain grows in a homologous series is you're adding an extra CH2 group. As a result of this growing chain length, what members of a homologous series have got is predictable patterns in physical properties. So they don't have the same physical property, but their physical properties are predictable. And what that means is that we can make statements, for instance, that the longer a chain, the higher the melting point or boiling point. And we can make comments about solubility as well. This is also affected by the chain length. So members of a homologous series, they've got the same functional group, which is the reactive part of a molecule. They've got the same chemical properties as a direct consequence of that. They've got the same general formula, which for alkenes is here. They grow by CH2 each time, and as a consequence of that, their physical properties, which is not reactivity, but as a result of having a longer chain, we can say that the molecule will have a higher melting point or boiling point. We're going to have a quick look now at the different functional groups, the different families that you'll encounter as you go through the AS level course. There are a few more at A level in the second year, but not actually all that very many, 4, I think, or 5. If we start with alkanes, the general formula for an alkane is CnH2n plus 2, which means you double the number of carbons and then add 2 in order to find out the number of hydrogens. So for instance, butane is C4, we need to double the 4 to get 8 and then add 2 to get 10. And that is the molecular formula for butane. Displayed formula, we've got 4 carbon atoms in a row. And each of those will have a hydrogen at each of the 90-degree angles. You can see why displayed formula is really slow. Structural formula faster, CH3, CH2, CH2, CH3, so definitely faster, but skeletal formula the fastest of all. That's the skeletal formula of butane. Now the functional group of the alkanes, really they don't have one. If you were pushed to say that they had one, it would be the carbon-to-carbon single bond, but that's definitely not unique to alkanes. That's in lots of other molecules as well, so really they don't have one. Now cyclohexane is also an alkane, but it's a bit different because that cyclo bit, as the name suggests, the carbon atoms are all arranged in a ring, not always a circle, but the cyclo bit means a ring structure. Now the formula of cyclohexane is C6H12, and what that means is each of these carbon atoms has got 2 hydrogen atoms attached to it as we go round. So this displayed formula taking quite a long time to draw. The structural formula and skeletal formula for cyclo compounds are actually the same thing, which is quite nice. And so what that is just drawing the shape like you would draw it in maths. So the structural formula for this ring of 6 is the hexagon, and the skeletal formula is the exact same thing. Looking at alkenes now, the general formula for alkenes we've already seen, it's CnH2n. So for ethene, which has got 2 carbon atoms in it, the number of hydrogens will be 4 because we double the 2. For pent-1ene, we've got 5 carbon atoms, and so the number of hydrogen atoms will be 10 because we just double it. Displayed formulae, we need to show that carbon-to-carbon double bond, and carbon atoms need a total of 4 covalent bonds, so we only have 2 single bonds to carbon atoms on each side. The structural formula, CH2, CH2. Sometimes you could get away with showing that double bond in the middle, but you don't need to. Skeletal formula, dead easy here. It's effectively an equal sign, maybe at a slight angle. Pent-1ene displayed formula, we've got 1, 2, 3, 4, 5, and the double bond is there, and we show the rest of the carbon to hydrogen atoms on here. Structural formula, CH2, CH, CH2, CH2, CH3 on there. Skeletal formula, 1, 2, 3, 4, 5 with an equal sign there. So you can see it's much faster with each of those carbons, 1, 2, 3, 4, 5. Halogenoalkanes, they are another homologous series that you are going to encounter in A-level chemistry. And what they have, they are effectively alkanes with a halogen attached to them, as their name implies. And so the general formula for them is CnH2n plus 1 X, where X equals a halogen. And the halogens, remember, are group 7, chlorine, bromine, fluorine, iodine, etc. The functional group is the carbon-to-halogen bond. The characteristics of that gives it its specific reactivity. Chloroethane is the first example I've got here. So it's ethane, so it's going to have 2 carbons, and it's going to have 5 hydrogens and then the chlorine, and they're going to be arranged in their displayed formula like this. And the structural formula, CH3, CH2, Cl. And the skeletal formula, that's for those 2 carbons, and then the Cl comes down like this. 2-bromopropane, it's propane, so it's going to be C3, and then it's going to be H7Br this time for the bromine. And then we're going to have 1, 2, 3, the bromine on here, and we're going to fill in the rest with hydrogen to make sure carbon has got 4 covalent bonds each time. And then structural formula, we've got a CH3, we've got the CH, then we've got the Br, and then we've got the CH3. Skeletal formula, there's my propane, and I've got the bromine coming out of the second carbon there. Moving on to take a look at alcohols now. The general formula for alcohols is CnH2n plus 2O, so exactly the same as alkanes except with the oxygen on the end. The functional group for alcohols is this OH group that we encountered earlier, and that is bonded to a carbon chain of some sort. That's where R comes in. R just means a carbon chain, but we don't know exactly what that carbon chain is. If we have a look at our two examples, we've got ethanol, which is C2H6O, sometimes written as C2H5OH, and that is us showing that we know it's an alcohol. The displayed formula for ethanol is here. The structural formula is CH3 for that first carbon, CH2 for the second carbon, and then it's got its OH sticking out of the end. And then the skeletal formula is that stick for the 2, and then OH coming out of the second carbon. Second example, we've got propan-1-ol, which is C3H8O or C3H7OH. But strictly speaking, the molecular formula is this. This one over here is kind of like a hybrid structural formula woven into our molecular formula. So the molecular formula is this one, C3H8O. The displayed formula would look like this, showing all of the covalent bonds. And the structural formula, CH3, CH2, CH2, OH. And then the skeletal formula, that's for our 3 carbon atoms in this chain, and then the OH up there. Our next homologous series we're going to have a look at is the aldehydes, and they have got the same general formula as an alkene, except with an oxygen on the end. And their functional group is this carbon chain again, and then we've got the C double bond O with a hydrogen attached to the same carbon. So effectively what this means is we've got this interesting functional group that always comes at the end of a carbon chain. Two examples again, ethanal, which has got the molecular formula C2H4O, and this is its displayed formula underneath. Skeletal formula CH3CHO. Note that we always put the hydrogen that belongs to that carbon first, and then we put the oxygen as well. That avoids any confusion that that hydrogen is attached to the oxygen. Skeletal formula, that line for those 2 carbons, and then again the double bond going down to the oxygen this time. Butanol is our other example, C4H8O, here is its displayed formula. Structural formula CH3, CH2, CH2, CHO. And skeletal formula 1, 2, 3, 4 carbons, so 1 at the beginning, 2, 3, 4 carbons, and then the double bond O going down like that, not showing that carbon to hydrogen bond at the end here on the skeletal formula. Ketones are really similar to aldehydes. In fact, they've got the same general formula as aldehydes. Their functional group is subtly different though. They still have that carbonyl group, this is called, that C double bond O, but it's not at the end of a chain, it's in the middle, which is why we've got these 2 R groups either side. So there's not 1 carbon chain, there's 2 carbon chains either side. And I've just put that 1 there and a 2 there to show that maybe these 2 might be different, or they could be the same. So an example where they are the same is propanone on the left hand side, and that's got the molecular formula C3H6O, and here is its displayed formula. Structural formula, nice and easy, I'm sure you've got the hang of this, CH3, CO, CH3. And its skeletal formula, chain of 3 again, like that, and the double bond O is in the middle. For butanone, our other example, C4H8O, the structural formula would be CH3, then CO, then CH2, then CH3. So the chain of 4, like that, in its skeletal formula, and then the double bond shown to the oxygen, like that. Carboxylic acids are what we're going to consider next, and carboxylic acids And carboxylic acids have got this functional group as shown on the right here. There is the carbon with that carbonyl group on it, but not only does it have the carbonyl group, it's got the oxygen and the hydrogen attached to it as well. So unlike the aldehyde, which only has a hydrogen in this position here, like the ketone, which has another carbon chain attached here, the carboxylic acids have got actually an alcohol group and a carbonyl group merged together. So they're almost two functional groups in one, but we call them one functional group. We call them the carboxylic acid functional group. And carboxylic acids have got this same beginning to its general formula as an alkene does, so double the number of hydrogen as you've got carbon, but then this time there's two oxygens in the functional group. So if we consider ethanoic acid, C2H4, double it, and then your two oxygens. The displayed formula is shown there. Structural formula CH3COOH. That's how you write the structural formula for a carboxylic acid. Skeletal formula for ethanoic acid, we've got our carbon-to-carbon bond like that, and then we go down to the oxygen with the hydrogen on it there, and we've got the double bond up like that. So that's the skeletal formula for ethanoic acid. For propanoic acid, there's its general formula down here. So we've got a CH3 attached to a CH2, and then we've got our characteristic COOH at the end. And skeletal formula, there's our chain of 3 carbons. There is our oxygen to hydrogen bond, and here is our double bond to the oxygen, like that. Now the last two we're going to look at, you're not going to encounter very frequently. The first one is amines. And I've never ever seen an exam question ask for the general formula of an amine, but there it is, CnH2n plus 3n. And so the number of hydrogen is actually greater per carbon than in any other general formula. And the reason is that the functional group is a carbon chain bonded to an NH2 group, and that is called the amine group. And you'll see that there are 2 hydrogens per nitrogen joined on. So we're going to have more hydrogens in the general formula. So if we have a look first of all at methylamine, C, double it, makes 2, add 3 makes 5, and then N is the molecular formula, and then the displayed formula is CH3NH2, and the structural formula is literally the exact same thing, CH3NH2. Now the skeletal formula, what's a bit weird is that the skeletal formula for a methyl group is a dot, because there's only 1 carbon. You're not even connecting anything together. But we do need to connect it to the nitrogen, so NH2 on there. So this is the skeletal formula for methylamine. Ethylamine is going to be really, really similar. It's going to have the formula C2H7n, and then here is its displayed formula. So its structural formula, CH3, CH2, NH2, like that. And then its structural formula, this time we've got 2 carbon atoms to join together, so there are those 2. And then we move down here, and that is our functional group there, the NH2. Now the last thing we're going to look at in this video is the nitrile family. And the nitrile family has got a funny general formula this time. It's CnH2n-1n. So the reason for that is that the functional group is this carbon to nitrogen triply bonded together at the end of a carbon chain. And so because the carbon has got a triple bond, then that means that there aren't as many spare bonds to the carbon atoms to accommodate more hydrogen. So there's fewer hydrogen than you might typically expect. 2 examples. If we have a look at ethane nitrile, we've got the molecular formula C2H3n, and then the displayed formula is shown underneath. Structural formula CH3CN, and the skeletal formula is the carbon to carbon bond shown like that, and then the carbon to nitrogen triple bond shown like that. Now this is a little bit funny because it doesn't follow the zigzag pattern that you normally get for skeletal formula, but the reason for that is that the angle between these bonds, this carbon to carbon bond here and this carbon to nitrogen bond, is actually 180 degrees, so we do show this in a line. And then finishing off with the second example, the butane nitrile C4H7n, we've got the CH3, CH2, CH2, CN, N. And then the skeletal formula, we've got our C to C to C to C, but again, this final C, this fourth one in a row, needs to have a triple bond to nitrogen. And you can show it connected as one long bond, which feels weird, but it is totally acceptable. And we know that there is carbon number 1, carbon number 2, carbon number 3, carbon number 4, and then that triple bond to the nitrogen on there. Okay, so that's the end of this introductory video to organic chemistry. Remember, naming organic molecules called nomenclature is coming in the next video, and then isomerism will be in the next video after that. Thank you very much for listening. Hope it's been useful. See you next time. Bye-bye.